All right, so in the hopes that you will get a little bit more out of this than you did in class, I'm going to go through the notes for the quadratic sequences one more time, a little bit slower, so that we can all understand how to write the equation for a quadratic function in standard form given a pattern in a table. So, quadratic sequences. And it is still 2, 22, 18. So the first thing that we talked about was arithmetic sequences. And arithmetic sequences have something called a common difference. Meaning that if you were to look at all of the y values of a arithmetic sequence or a set of numbers in arithmetic sequence, you would add or subtract to get to the next term. However, geometric sequences were a little different. With geometric sequences, instead of adding or subtracting to get to the next term, we multiplied or divided. In that case, we call that a common ratio. Hopefully from class, you remember that to create a quadratic function, we are essentially taking two linear functions and finding the product of them. In that case, since arithmetic sequences are the same or similar to linear functions, it would be fair to suggest or to assume that a quadratic sequence is going to have some relationship to an arithmetic sequence. With that in mind, we're going to start talking about quadratic sequences. So, with quadratic sequences, we're going to actually look at one and discover what exactly a quadratic sequence has. So I'm going to treat this as though I assume that it is an arithmetic sequence. I'm going to find if there is a common difference. So to get from 17 to 11, I would subtract 6. To get from 11 to 7, I would subtract 4. To get from 7 to 5, I would subtract 2. To get from 5 to 5, I would subtract 0. And to get from 5 to 7, I would subtract 2. Now, unfortunately, as we can see, there is no common difference. However, hopefully you notice that there's a pattern with these numbers. If I were to take the differences one step further, I would notice that between -6 and -4, I'm adding 2. Between -4 and -2, I'm also adding 2. And that same pattern continues. Okay, what we can call both of these rows, okay, we can call this the first difference. Now, if those had been the same, we'd be able to say that it was arithmetic. However, because they are not the same, we cannot call it arithmetic. What is the same, though, is our second difference. And that's what we look for to determine if a set of numbers is in fact quadratic. A common second difference. Okay. So the next thing we talked about in class was what exactly the form of a quadratic sequence should look like. And what I had you guys do was turn all the way back to the function notes from October 3rd, where we talked about the function family. And what we focused on specifically was the standard form of quadratic function, which is y equals, and I am going to write the specific letters in a different color so we can focus on them. ax squared plus bx plus c. Now, the reason that I did those in a different color is because these letters are what I'm looking for. The reason we are looking for them is because right now there are unknowns. We should be able to find a y and an x since we are given an entire table of values, but we don't know what a, b, and c is for this relationship. And there's a really quick way for us to be able to do that. I'm going to draw a line so we can talk about how exactly we get there. So we're still going to be using the same relationship, so even though you might not be able to see it on my screen, it's important that you know that's still the same relationship that we're using. So I'm going to come back down here and I'm going to write my standard form of my equation. Okay. Now, the a value can be determined by taking our second difference and dividing it by 2. That will always work. Okay. My c term is also my 0 term. And if we were talking about this in terms of just a quadratic function, a linear function, or an exponential function, we call that 0 term our y-intercept. Okay. Now, there's no fancy way to find b, but we do already know y and x. We can take any point from the table and use them. So what I like to do is I like to come down and I like to define some of my variables. So I know that I need to find a, b, c, x, and y. Okay, so I know from up here that my second difference was 2. And I know to find my a value, I take my second difference and divide it by 2. In this case, it would be 2 divided by 2, which I can simplify as 1. Okay, I don't know b yet. Okay, I'm going to outline b because that's the special one. That's the one that we actually have to do some math to find. Okay. C, however, is my 0 term on my y-intercept. If we go back and we look in our table, we should be able to see right here, okay, and I will circle it. This would be considered my y-intercept. So I know that C is 7. Okay. At this point, we can pick any point in our table. The only one that I suggest against is the y-intercept, just in case you make a mistake and you don't choose the right C term. It just helps to kind of avoid that confusion. So I'm going to choose the point 1, 5. But again, you could choose any point you wanted to. So I now have y, a, x, x, and c. The only one I'm missing is b. Because of that, I'm able to actually solve backwards to find that missing value. So I'm going to start with my standard function. And I'm just going to plug in what I know. I know that y is 5. I know that a is 1. I know that x is 1. Okay, I don't know b, so I'm going to leave that. I do know that x is 1. And I know that c is 7. Okay, from here, I can just begin to simplify. 5 is still 5. 1 squared is 1, times 1 would still be 1. b times 1 is b, and 7 stays the same. From here, I have two like terms. I've got 1 and 7. So 5 is equal to b plus 8. And the last step to getting b alone would be to subtract 8 from both sides, which would leave me with -3 is equal to b. And I'm going to take that number and I'm going to write it over here. Okay, what's important to remember is that if I look back up here at my quadratic function, what I'm trying to do is replace a, b, and c. I don't want to replace y, x, and x, because then I would just have an equation with a bunch of numbers in it. I need to have those input and outputs available so that I could input anything in there. So I'm going to come down here and I'm going to outline those three letters because those are the ones that I want to replace. I want to write my quadratic equation replacing a, b, and c. So what I would have is y is equal to 1x squared. Okay, and you can write the 1 if you want to. I'm choosing not to. Minus 3x. I replaced my b with -3. And then plus 7. I replaced my c with my c value. And what I have here is now the quadratic equation for the following table that was written above. If you were to plug in any of the terms from that original table, it would all work out. Okay, so this is the quadratic function that represents the table above. I hope that made a little more sense than in class.